All right, this is a rate in, rate out problem, and we're told that the rainwater is flowing into the drain pipe at this rate R of T. And that's in cubic feet per hour, T is in hours, time is 0 to 8. Pipe is partially blocked, so the water drains out. So here's the out at the D of T. Again, that's in cubic feet per hour, still on 0 to 8 hours. There are 30 cubic feet of water in the pipe at time equals 0. So how many cubic feet come into the pipe on the 8-hour time interval? Well, that is going to be the integral of your rate in function, R of T, on 0 to 8. So if we go to our calculator and we go to our graphing screen, under Y1, we're going to plug in our rate in, which is 20 times sine of, and don't forget you have to use X. You can't put T in your graphing screen of your calculator. And while I'm at it, I'm going to go ahead and plug in under my Y4. I'm going to plug in the rate out because I have a sneaking suspicion we're going to need it. So negative 0.04 x cubed plus 0.4 x squared plus 0.96 x. Okay, so now I need to go back to my home screen and I need to integrate using alpha F2, choice 4, and I'm going to integrate from 0 to 8 the y1 function. So vars, y-vars, function y1. Integrate with respect to x and hit enter. My answer is 76.570. 76.570. And that is in cubic feet of rainwater, so feet cubed. Okay, next they're asking us, is the water in the pipe increasing or decreasing at time equals 3? Well, in order to find that out, I basically need to take rate in minus rate out and evaluate that where time equals 3. So it says, is the amount of water increasing or decreasing? Well, you need the derivative for that, but they gave us the derivative. R and D are both already rate functions. So we really don't have to differentiate it. We definitely don't have to differentiate anything. So I'm going to try doing it like this. Vars, y-vars, function, and then y1. And I want to evaluate that at 3. Let's see if that works. There we go. That's the rate at which water is entering at time equals 3. I'm going to do the same now for the rate at which water is leaving. So that's my y4, and I will evaluate that at 3 as well. So that's the rate at which the water is leaving. This is negative, okay? Now I would go ahead and write down what they are. We have 5.086 minus 5.4. That is negative. And so you're going to have to write that the amount of water in the pipe is decreasing at time equals 3 hours because R minus D is less than 0. All right, part C. At what time is the amount of water in the pipe at a minimum? Well, this is where you'd have a table of values. You'd have your time, and then you'd have the amount of water in the pipe. And you know that 2 of the times you need to look at are 0 and 8. At time equals 0, we're already told that there are 30 cubic feet. This is the amount of water in the pipe. So there's 30 cubic feet here. I next need the critical point. I need to know where R equals D. So I'm going to write down this. Solve for where R equals D to find the critical point. That's where the derivatives are equal to each other. I can go to my graph screen and let's just see if I can see the whole graph. I know I have the interval 0 to 8 here shown on the Zoom 6. And I don't think I see enough here. So I'm going to get a better window and perhaps just go from 0 to 10 and then maybe 0 to 20 on the y-axis. Okay, so the calculator is graphing that window I just put in, which was from 0 to 10 and 0 to 20. And I have 2 intersection points, but let's take a look here. We have second calc. We're going to do intersect, and let's move our cursor towards the first point of intersection and hit guess 3 times, and we get it at 3.2716. So 3.2716, and let's go back and make sure I did that right. 3.2716. Yep. Okay, let's check the other intersection point that I see here on my screen by moving all the way along my graph over to it. And then I'll hit guess 3 times as soon as I get there. And this other intersection point, look at that, it's at 9.463, which is outside of the given interval from 0 to 8. So I just have 3 points I need to check. And actually, I already know the value at the first point. At 0, we had 30 cubic feet. So let's go back to the home screen. And what we're going to do is we're going to integrate. And we're going to integrate from 0 to 3.2716. That's our critical point. And we need to integrate rate in minus rate out. So remember that rate in was stored in y1 and rate out was stored in y4. Oops. Once again, I forgot my x to say that I'm integrating with respect to x, so I pull that back. Now this is the total change. Remember that we started with 30, so I have to add 30 to the total change to find out that at time equals 3.2716, we had 27.964 or 5 cubic feet. Now we've got to do the same thing for time equals 8. So I basically just need to go back and grab this expression and change my upper limit of integration to be just the value 8. And remember that this is the total change from 0 to 8, and I have to add to that the initial value of 30. So that's 48.544. Now, the question said, at what time was the amount of water in a pipe at a minimum? So that's going to be at time equals 3.2716, and that's in hours. Your justification is this table of values. There's nothing you have to write, okay? Last part says, the pipe can hold 50 cubic feet of water before overflowing. For time greater than 8, water continues to flow into and out of the pipe. They want you to write but do not solve an equation involving one or more integrals that gives the time when the pipe begins to overflow. So here's what you want. You want the 30 cubic feet that you start with. Then you're going to integrate from 0 to some time, we'll call it x, and then you need your integral is going to be the rate in minus rate out, and you're going to overflow when you get to 50, so you need to know when that total sum of the initial value plus the integral of rate in minus rate out is equal to 50. And this will be your answer to D.